is just a little bit. Okay, so one of the things that makes all these patterns happen the way they do on the periodic table, obviously it's the number of electrons in the outer shell, how many energy levels are present, because the more energy levels, the bigger the atom gets. And then there's something called effective nuclear charge, which is really important in how the atoms, or I should say even the ions, behave. So first of all, I should figure out what it is. It's basically called effective nuclear charge, and it is the net positive charge experienced by the electrons in an atom. So it's how that positive charge of the nucleus, this net positive charge that's in the nucleus, because the protons give it to us, so it's in the nucleus, experienced by the electrons in an atom. Where are the electrons? They're in the valence shells. Or we could say energy levels. So effective nuclear charge is how much the electrons feel the positive charge of the protons and are pulled towards the nucleus. We can say the greater I'm just going to say effective nuclear charge, the greater the ENC, the more the electrons are pulled towards the nucleus. So now get your lab paper and find the part about atomic radius. So let's look at effective nuclear charge and atomic radius. So basically you should know by now, atomic radius is kind of like how big the atom is. That's, you know, we can say it's half the distance between the nuclei of two bonded atoms, or we can say how big the atom is. I want you to look at your paper, and I want you to tell me what is the trend that you found as you moved across the periodic table. What happened to atomic radius as you moved across the periodic table? When you know, stand up. What happened to atomic radius as you move across the periodic table? Megan, what happened as you went across the periodic table? Across the periodic table, not down.
It
Okay, so are you saying on the, I gotta think about right and left here, this is difficult. On the right-hand side, it's smaller than on the left-hand side?
No, like left side to right side.
Okay. Do people agree with her? That increase from left to right? From group 1 to group 17, did it increase?
I was looking at mine on the
Okay, that's all right. Now flip to your atomic radius.
Yeah, flip that.
So how does it, Josh, what does yours say? I want to see if you guys agree with each other.
Oh, the decrease?
Okay, go to your lab stations. Woo. Go to your lab stations and pull out one of those atomic radius 3D models. Everybody find, once you get one, find sodium. It doesn't matter, just do it quick. You don't even have to do it to the lab people you worked with. Just grab one and look at it. See if you agree with them. From group 1 to group 17, now that you've all looked at it, Kirsten, tell me what happens.
It decreases.
Good. Now you can sit down. I know you're all asleep, so I'm going to make you walk around today. Across the periodic table, atomic radius decreases. What happens to the number of protons in the atoms as I move across the periodic table? What?
Increases?
Yes, it increases. So, as I move across, ooh, what are those things called when we move across the periodic table? Versus down? What?
No, group is this way.
Group is this way, period is this way, yes? So across the periodic table, or across the period, the number of electrons increases. Josh is correct. What happens to the energy level? Does it change as I move across, or does it stay the same for the whole period? What did we learn? What do we put on our periodic table? Period 1 uses what energy level? Period 2 uses what energy level? Or ends in? Period 3 ends in what energy level? If you don't know, you should be looking at that table that we put all that information on. Who knows? I'm not going to tell you. You're going to have to figure it out. Are you looking at it, Maddie?
Isn't it just like as it goes down, it goes up one?
Yeah, as it goes down, it goes up one. So what about if I'm at, let me pick an element. If I'm at, we'll go back to sodium. Look at that table. If I'm at sodium, what period is that? Rowan, what do you think? What period is sodium in? Thank you, Rowan. It's in period 3. Lindy, what energy level does period 3 use? Yay, 3. Woo! You guys are making me nervous today. Okay, so they're all in the same energy level, right? As I move right across period 1. Everybody look at period, no, let's look at period 2. Everybody look at period 2. Find your periodic table, find period 2. If you can't do this stuff, you're going to die on the test. So, in period 2, all the way across that table, I stay in the second energy level. When I go to period 3, which starts with what? Sodium. All the way across, I'm in the third energy level. So period tells me the energy level. So as I move across the period, the number of electrons increases, the energy level that they're in stays the same. So as I'm adding those electrons, there's a greater pull towards the nucleus because there's more protons. That's why it decreases. The number of protons goes up, the energy level stays the same. That was painful. Let's try the flip side of it. Let's look at, can I flip this page? We good? Let's look at down the periodic table. So that's moving down a group. What happened to atomic radius? Write that up there. As I moved down a group, down the periodic table, or I could say down a group. So let's pick a group. Let's pick group 2, which starts with beryllium. As I move down the periodic table, what happens to atomic radius? Annika? Yes, it increases. Now, is there anybody in this room who wants 5 bonus points? Ooh, a couple brave souls. I'm going to give you 5 bonus points if you can tell me why that happens. Think about it. If you think you know, raise your hand. Okay, Josh.
Because you're adding another energy level.
Yay, Josh! Wake up, people. Wake up. Because you're adding an energy level. Woo! Because we add an energy level. And then think about this, as I add an energy level, it gets farther away from the nucleus, right? Every energy level is a little farther away. So do they feel that effective nuclear charge as much? Way out there? No. That's why it gets bigger. So that's the why. There was a question, I think it was number 7, and I said we can't answer all these things until we talk a little bit. That's one of them. Now, we've done atomic radius, which was first. Look at that paper. What's after that? Is it electronegativity? Was that the second trend? I don't remember how I typed them. Ionization energy was the second trend. Okay, so let's talk about that one next. We'll work in order. Okay. Anybody remember what ionization energy is? And if you don't, you wrote it on your paper so you can read it. Lindy, tell me what ionization energy is really loud.
Energy needed to overcome the charge of the nucleus, and the negative charges for the electrons, and the electrons.
Okay, good. So, let's make that a little shorter, if we can. I'm just going to say it's the energy required to remove an electron from a neutral atom. Now let's find our trend after we get done writing that. I want you to go to your lab and I want you to find the trend across the table. So look at your paper, or if it helps you, get up and look at one of the models and see what's the trend for ionization energy as I move across the table. Faith, can you tell me?
It increases.
Yes, it does. It increases. So across the table, those straws should have gotten bigger. Why would that be? Mara?
Because they all want to get the 8 electrons in the
Good. Excellent. So here, the reason it increases is because, let's just say, the closer to group, what are the weirdos that hang out on the side of the periodic table that don't fit any of this stuff? Group 18, who are they? Noble gases, good. The closer to group 18, the closer to a full outer shell. So electrons are held more tightly, or it takes more energy. You can say it either way. They want to hold on to them. So what happens then? What's the trend down the periodic table? What happened? Look at your numbers, or look at your handout, or get up and look at the little model. What happens as I move down the periodic table to ionization energy? Carter, do you know?
Top to bottom it decreases.
Good. It decreases from top to bottom or down the table. Why does it decrease? That's a little harder question than the last one. Why do you think it decreases? Anybody want to guess? Or give me an answer? What happens as I move down the periodic table to the size of the atom? What's being added? Energy levels. So if I have more energy levels, those electrons I want to grab are farther away, right? So there's less effective nuclear charge. So they're easier to take away. So as we move down, energy levels are added. Electrons are farther, bless you, from the nucleus. They feel, whoops, not fell, they feel less effective nuclear charge. So they're easier to remove. Okay, let's take a break for a minute, and I want you to get together with your lab partner, and I want you to answer the why, and really answer it well on number 7 for those two trends. Like, answer it all the way. I'm really going to look at that when I grade those labs. Then if we have time, we'll come back here and get the last two.